Alright, so I guess what I'm going to do for the rest of this, we're going to do a centre of gravity test on this car, and the Rockfield, one of the Rockfield engineers, so they're a consultancy firm, is actually bringing out some force sensors so that we can actually do it properly. But technically we can do that. We could do that if it was light enough on like 4 kitchen scales or 4 bathroom scales. And I've got a set of kitchen scales here, and we'll do something in a second that's sort of a classroom version of it. So we can work out where the centre of gravity of just about everything is. But what I'm going to do first is how that works. So have you guys done anything to do with force and moment and conservation thereof, equilibrium of force and moment? Right. So that's really fundamental first year engineering stuff that I'm going to go through a very, very simple example on the board. That'll bring you up to speed with that. Now, in terms of what you can do in a classroom, you don't need to go through this theory because, as you'll see, it actually ends up being a ratio equation between, so if you have a board and a force somewhere, the ratio between this side of the weight and this side of the weight is the same ratio that you get in your reaction forces, which would be what you'd be reading on your scales. And you can do all of that kind of stuff in a classroom setting, but I'll leave that up to you guys as to how you kind of break it down. But for you guys, I thought it was worthwhile going through the engineering theory, and then you can simplify it however you see fit. So what we'll be talking about, the main ideas come from trigonometry, force equilibrium, and force is obviously in newtons, and moment equilibrium, and that's in newton meters. And so force equilibrium is basically sum of the forces equals 0 if something's not moving, and sum of the moments equals 0 if something's not moving for moment equilibrium. Do you guys know what moment is? Have you ever talked about that at all? Moment is basically force with a lever arm. So moment is what's going to rotate something. If I was to take my board here, and I was to put a weight on the end, or it's got its own weight, but force is obviously the force down that the weight's doing, and so I need to both hold this up by that amount of force, and I also need to stop this rotating. And the amount of moment in newton meters that's trying to rotate by is the force by the lever arm. Alright, it's kind of like torque as well. So I need to stop this rotating by that force times that lever arm in terms of moment, and I need to stop it falling if I'm pushing down on it by that amount of force up. And so if I can do that, the force up and force down will be equal, and that's static equilibrium for the force, and the moment that way and the moment this way will be equal and cancel out and equal 0, and that's static equilibrium for the moment. And those are basically the fundamental underlying principles of engineering statics. And so let's say I'll make these notes available obviously if you feel like not writing it down, either way. Alright, so if I was to draw up the example that I was just talking about with the beam sticking out from the wall, and we call this end 0, and this is the wall. We have force down on the end, like I was saying, and we assume that there's a weightless beam for the moment. Length L. If we know F and L, we can basically calculate everything else. And that's what I'm going to do now. And the question might be, alright, so what reactions of the wall maintain the static equilibrium of the beam? So what's stopping that beam from falling and rotating in terms of reactions? Because from an engineering standpoint, those reactions are very important because they relate to stress and force and how that's translated through the beam and all that kind of stuff. what we do is draw a free body diagram, which is that same beam redrawn with an F on the end and some sort of dimension, L. Always draw our axes. And then, so what we draw over here are our reactions, what the wall is actually doing to that beam to hold it up. And then if you draw those correctly, then the beam shouldn't be moving. If you get them wrong, the beam will be moving. So if the force is down, then we automatically assume that our reaction will be up, but it doesn't need to be because we'll calculate what its value is. We'll say that this is O, so this is point O, and so that's the reaction at O in the Y. We could have an X, but we know there's no forces in the X, so we're not going to bother drawing it. And then we'll have a moment over here, M at O, which rotates around that point, and that's counterclockwise, because if we look at this, we have a force in the Y down, which means our reaction has to be up to stop it from going down, and we have a rotation, or moment, around 0. In this case, that force is causing it to go clockwise. So clockwise. And we use the right hand rule. So right hand rule in the direction of the Z. So at the moment, that clockwise is a negative moment. This one needs to cancel it out, so it adds to 0, which will be a positive moment. So you have positive there, negative there, and they'll cancel out to be summed to the 0. So generally we try to draw them right just to start with, but it doesn't really matter because once we actually do the calculation, if you come up with a negative number for one of those, it just means you've drawn it backwards. Okay. And then we apply our two equations. So sum of the forces in the Y equals 0 equals negative F, because we're going positive Y, negative F, and then plus R OY. Therefore, rearranging that, ROY equals F. We know F, we know ROY. Easy enough. And then our sum of the moments equals equals 0, equals the force times its lever arm. So we need a point when we're calculating moment around which we're calculating. And any force with the lever arm out from that will create a moment. Alright? So force out here has a lever arm of L, and because that's negative, if we look at our X, Y, Z would be out of the page, so that's negative. So we have negative FL as that moment. We've got a force here. Does that have a lever arm? If you think of, if you're going around that point, if you're pointing straight at that point, there's no lever arm. That force can't rotate anything because it's pointed straight at that point, so it doesn't have a lever arm, so it can't exert any moment. And then we've got this moment that the wall's exerting, which is an applied moment, and because of our right-hand rule, we're saying that's positive, just the way we've drawn it. So that's going to be plus MO. Then we rearrange this equation because we know F and we know L to MO equals FL. Alright, if we know F and we know L, we've got our reaction force and our moment. Alright, and that's what the wall has to exert on that beam to hold it up. Alright, so that's a very, very simple version of forced equilibrium for a shaft like that, or for a beam, which is exactly what we're going to rely on for the centre of gravity test. So I'm going to get a little bit more complicated now, just in terms of two reactions rather than one, and then we're going to convert that to our car and work out how we actually calculate where the centre of gravity is. Alright, so in this example, it's exactly the same procedure, except now we're going to do a beam that has two simple supports rather than a wall. Alright, so rather than something stuck to a wall, I've got what's called a simple support here and a simple support here. That's just a pin. Right? So the main feature of a simple support is that if it's on a pin, it can rotate. So if I chop this beam in half, both those ends of the beam would just flop down like that. Okay? And so if that's a free pin, what it means is that the pin can't resist any moment. with a wall over here could resist moment because you've welded it to the wall or you've bolted it or whatever. Over here, that can't resist any moment, so moment at those 2 points have to be 0 because it's a pin. If I put a pin, if I attach this with a pin to the wall, obviously the force would just, flop it down and that'd be the end of it. So it needs something that can resist that moment. When we've got two supports, we don't actually need that, because if I was to put a force in the middle, let's say that force is 1,000 newtons, then those two pins will still hold that up, because the beam itself is resisting whatever moment is there because of the stiffness of the beam. Let's call this A, call this B. Let's say that force is applied off-centre. So let's say 2 metres and 3 metres. So it's applied just a bit to the left.
Those pins are right at the end?
Yeah, right at the end. Alright, and what are the reaction forces at A and B? Now, if you look at that, and then you look at my bit of wood there, and you think of 2 kitchen scales or 2 bathroom scales or something like that, you can actually measure what the force at A and B are if you put some weight somewhere. Alright, so that's where we're going, just so it sort of grounds it a bit. Alright, so as before, we do a free body diagram, which is just our beam, our force off centre there of 1,000 newtons. Two reactions at each of those pins, RA in the Y and RB in the Y. Every diagram we ever draw as an engineer needs one of them. And I'm still telling them when they're about third years that every diagram they ever draw needs one of them. So don't listen, but that's okay. 2 metres, 3 metres. Alright, and now we can do the sum of the forces and some of the moments around a point and calculate what we need. So, some of the forces in the Y. Now if we had X forces as well, we'd have to do some of the forces in the X and Z and so forth. Some of the forces in the Y equals 0 equals RAY plus RBY minus 1,000. Rearranging that, 1,000 equals RAY plus RBY, which is obviously indeterminate because we have 2 unknowns in one equation. And so where we get the second equation from is our sum of the moments. Sum of the moments, and we can do any point. We could do some of the moments around this point, we could do some of the moments around this point, we could do some of the moments around this point. But where we choose to do some of the moments around has to get rid of one of those reaction forces, or it's ideal if it did. Alright? You could still probably calculate it because you'd have 2 equations and 2 unknowns and you'd rearrange it. But if we do some of the moments around this point, remember that this doesn't have a lever arm anymore, and so that's not in the equation. And so I only have one unknown in the equation, I could automatically calculate. It's just quicker. So we're going to do some of the moments around that right-hand point there. So sum of the moments around B equals 0 equals 1,000 times its lever arm here, and its lever arm is 3 metres. And by our right-hand rule, that's a positive moment. And then I'm going to do RAY times its lever arm, which is 5 metres. And because it's going that way, it's rotating it that way, it's a negative. So minus RAY times 5. And then if I rearrange that equation, I get RAY equals 600 newtons. And sub all of that stuff back into here, and I get RBY equals 400 newtons. Alright, now let's have a look at those numbers for a second. What's the relationship between the 600 and the 400 number in terms of a ratio? 2 to 3. And if you look at our lengths here, and you look at which one's which, RBY is 400, is the lesser. And that makes sense because the closer the load gets to something, the larger the reaction force should be, to a point where if it was 1,000 here, RA would be 1,000 and RB would be 0. Yeah? So whatever the ratio here is, it's the opposite ratio for the forces. Right? And you can still do some of the forces to work that out, because RAY and RBY have to add up to 1,000. But if that's 3:2, then we know that by a ratio of 3:2, that 1,000 needs to be distributed on the reactions. Right? And so if you don't want to go through all of this, some of the forces, some of the moment stuff, which is fairly advanced first year engineering type stuff, then you can just talk about a ratio and you can still get the same sort of calculation stuff going on. It's up to you. All right. So you can see where I'm going with that, because before we start talking about a car, which is just the advanced version of this, if I have a scale or two scales and some sort of weight and some sort of board, we can reproduce all of this. I'm not sure. I'm just going to do this. Tested this so it won't prove me to be wrong. Put something under that. Ideally I'd have two scales, but I only have one scale. It just occurred to me that I can actually do this in practice this morning, rather than just give you the theory. Now, one thing we've got to remember is scales measure in grams or kilograms. And so what you actually need to have a chat with students about is the relationship between F equals mg and what force is as opposed to mass. Basically, a scale is reading force and then converting it to mass because it's a linear relationship through gravity. So you can talk about all that sort of stuff. All right, so if I'm going to zero that, the other thing is that with one, it still doesn't matter that I'm only reading one side, because through these relationships, if I know one and I know how much this is, then the other one's just going to be the difference. So ideally, if I put my 1.25 kilogram weight, it's obviously in ideal situation here, somewhere in the middle, I should get roughly half of that. And I'm reading 607 grams there, come a bit that way. Yeah, so it's a bit off there, but what am I looking for half of that? About 600. Yeah, it's better off. So automatically there, I'm reading the right thing. Now what you can actually do in a classroom situation is not have a really dodgy version of this. You can have a nice beam with two scales and things like that. As I said, it just occurred to me that I actually have this here this morning as a test. But you could get the students to chuck a weight on a quarter of the way along and get them to calculate what they should expect on the scales, and then get them to read it and actually see that what they're calculating is correct. Alternatively, you can go the opposite way and say, all right, I want to read a certain amount of value on this scale and a certain amount on that scale. Where do I need to put my weight on the beam, and get them to do that as well. And so there's a little bit of simultaneous equations there. There's a little bit of force equals mg. There's all of that kind of stuff that you can actually do in a classroom example that can fit into whatever context you want it to fit into. And then, of course, you can get a more advanced version of that and start talking about the centre of gravity like we're going to, because you do exactly the same thing for the centre of gravity. Because what the centre of gravity is of anything is an equivalent point in that item where if you applied all its weight, then it would have exactly the same effect on wherever it's touching the ground as if you distributed it over the entire thing. That's the point of the centre of gravity. So we're going to talk about a car, but you could just as easily do a table, or you could do a chest of drawers, or you could do something that you could put on 2 or 4 scales in a classroom. Where is the centre of gravity in the horizontal, and also where is the centre of gravity in the vertical, which is the more complicated thing where we need some trig and we actually raise up one side. So I'll give you the equations for both of those, and then hopefully our car people will be ready to do some testing. Alright, so what we're going to do now is exactly the same thing, except we're just going to visualise it as a car. Badly drawn car. Call this A, call this B. And our centre of gravity for that car is somewhere across the horizontal between A and B. And so what we will actually get is reactions at A and B at the contact patch of the tyre, RAY and RBY. Now obviously you have 4 tyres, so you'll have RAY left and RAY right, but added together that's just the reactions at the front. Alright, so that's what we're going to do. You can actually work out what you do for a race car or any type of vehicle. You work out where the centre of gravity is this way, you work out where the centre of gravity is horizontally, and you work out where the centre of gravity is vertically. It's very important for any type of vehicle because that tells you a lot of your performance characteristics. For a race car, that centre of gravity needs to be as low as possible because the higher it is, the more you're going to tilt in the turn. So the lower it is, the more squat and the faster around corners you can actually go. Alright, so this force equals mg. And we have some measurements, x1, x2, and we should know what the actual length of the wheelbase is, L. And now if we put a car on a set of scales, what we could actually read is we'd be reading RAY, and we'd be reading RBY, they're measured. And then we need to do some of the forces, some of the moments to work out what x1 and x2 are, which is exactly what we're doing over here, except we've got slightly different unknowns. Okay, so force. Sum of the forces equals 0 equals negative F plus RAY plus RBY. Therefore, F equals RAY plus RBY. Right, we read both of those so we can calculate what F actually is, which is just the force of the car, which is the mass of the car times roughly 10. And then x1 equals something and x2 equals something. Everyone should be able to do this by now, hopefully, but some of the moments, and let's do some of the moments around B again, same as what we did before. Equals 0 equals our F times its lever arm, which is x2. F times the lever arm x2 minus, so that was positive, this one's minus, RAY times its lever arm is L. Times L, and then rearranging that, x2 equals RAY L on F, and because we're going to relate F back to what we're actually measuring, RAY L on RAY plus RBY. X1 equals L minus x2. Right. And so now we've worked out where the centre of gravity is in that horizontal dimension. Right? And you can do that with just about anything. So with 2 scales or 4 scales, you can measure the centre of gravity in the horizontal very easily with a very easy set of equations of just about anything. Now the more complicated part is the how high is the centre of gravity, because you have to raise one wheel up or raise one side up. The reason that works is because this has a distance here and I have weight. Now if I raise one of those sides up, this, by whatever height, moves that way and the distribution of weight on the wheels change. Right? So as you have something, if the centre of gravity was perfectly horizontal, the distribution would change perfectly, would basically stay exactly the same. But as that raises up, as you raise it, over here, the centre of gravity moves over. And to a point where, at some point, the centre of gravity is now above that tyre, and you've got all of the force on the front tyre. Right? Obviously that's an ideal because then the car tips over. But by doing that, and by using trigonometry, and the new distribution of weight and the old distribution of weight, you can calculate what the height of that centre of gravity is. It would be a good project for a first year engineer to actually derive that. Alright, so, for example, and this is the last thing we need to do on the board. How high is the COG. And I might start over here so I have a bit more room. Alright, so if I have my horizontal there, my front tyre here, back tyre there, then what we're actually going to do, because this contact patch isn't directly below that anymore, we're going to calculate the height above the centre to centre line of the wheels and then just add the radius of the wheel because it actually moves around once you actually start rotating that wheel. So it's exactly the same thing, we're just going to use the centre line of the tyre. This is some angle, which you just get from, what we're going to do is stick this on some bricks and then measure the front weight once we change it over. So whatever that angle is, you can calculate. We're going to have a reaction force here, which is technically applied at the axle, at A, Y, and I'm just going to put dashes on everything in this configuration because the previous configuration we just used non-dashed form. Right, my centre of gravity is now moved over here to the left, but it's still applying down.
What does that funny symbol mean?
That's just a symbol that represents the centre of gravity. So when you have the centre of gravity, it's just a first year engineering thing, what they learn. Basically, that's the direction of the centre of gravity, and this just means that this point here is the exact point in space where the centre of gravity is. It's just a kind of a nomenclature. Alright, so this height is the one we're interested in, H. And then we're going to add the radius to that so that we know the true centre of gravity. Actually, I think I'm calling this H dash in this particular derivation. Okay, so let's put a dash on that. And then obviously over here we would have a reaction force as well. RBY dashed, that's B. And we have some new dimensions. So the new position of the centre of gravity is shifted over to the left. We call this x1 dashed and this x2 dashed. And this distance here is no longer the length of the car because of trig. This is L dash, which is just equal to L cos theta. Right. So, the first step, we can work out what x1 dash and x2 dash are. It's exactly the same as what we did before. It's tilted, but because all the forces are down, the lever arm of a moment is right angle to the direction of the force, so it's technically we can still calculate in the horizontal plane because all those forces are still down. It's just a slightly reduced case and it's moved over to one side. Alright, so the length is a little bit less and it's moved that way. We can calculate what these are, and using exactly the same force and moment balance as what we did, we can get what x1 bar and x2 bar are. If I know x1 bar, that's this, and I know what this angle is, I can get this measurement. I know that that angle is the same up there. And so if I have this to this measurement, and I also have this to this measurement, because that's x1 in the previous example, that's what we calculated, where it is regularly when it's horizontal, I can calculate what this length is. And using trig, if I know what this length is, I can calculate what that length is, and then I've got my h dash, I add my radius to it, and I know my centre of gravity. So that's where the actual trigonometry comes into it as well. Yes, absolutely. So, are you on board with calculating x1 bar and x2 bar? Yeah?
Just the diagram.
Yep, so if I have that length there, and this is a triangle, this is a right angle triangle, using trig with this angle, I can calculate that length. And if I can calculate that length, I know this length from the previous example. I can subtract one from the other and I get this length, and then with trig, I get that length. Alright, so this is the force moment equilibrium step, which is our sum of the forces in y equals 0 equals ray dash plus rby dash minus f. Exactly the same as what we did before, ray dash plus rby dash, which is technically just the weight of our car, or the weight in terms of force, which is what we measured before, ray plus rby. That's exactly the same. The distribution will be different, but the total weight of the car doesn't change, so we already know that value. And some of the moments around B, let's say, on the back tyre, equals 0, equals our force, F over here, which is mg. Force, x dash 2. So that's a positive down, because we're doing it around the horizontal plane, because it's all acting like that. And then ray will be a negative over here. So that's minus ray dash times L dash. And if I convert some of my dash stuff to things I know, I'll do that in a second. We'll rearrange this. x2 dash equals L dash on F. And I'm going to get rid of F because I know that F equals these two things, which we already know. I'm going to get rid of L dash because L dash is just a relationship to the actual length, which we know. So the real equation for x2 dash equals ray dashed L cos theta on ray plus rby. Alright, and then x1 dashed equals L dash minus x2 dashed. Therefore, x1 dashed equals L cos theta minus x2 dashed. Right. And if you look at this, because we've done sum and moment around the back tyre, we only actually need to measure the weight at the front. We don't need the weight at the back or the force at the back this time, because we already did that from the previous one. We already know what the total force is. And when we're doing some of the forces around the back, it makes that RBY go away. So all we need now is to read one value at the front, and I can get my distribution of x2 dash and x1 dash. The last thing is to do all of that trigonometry that I said. So let's just modify this. Call that the trig step. So you can draw this diagram again if you want, whatever. The main part is that. Any more? Here. So the main thing is that I'm going to call this measurement here B, and I'm going to call this measurement here A. And we're going to note that A plus B equals x1 from the previous calculation. Alright? And I know x1, which is this. So x1 to B, B to A to H, and I've got my solution.
And then you're going to do that for Z direction as well?
We could, if we wanted to, but I'm not going to bother. So
But that's how you would do it?
that's how you do it. Well, at the moment, once you've got the height, you sort it. So height is one dimension. We've got it this way. All we need to do is that first calculation for the horizontal position. Ideally, it should be in the middle. If it's not in the middle, then you've got to...
But the driver's on one side of that?
True. Yeah. So on the actual race car that we're talking about, it's centre. It's like a Formula Ford or like a tiny little F1 car. So driver's centre, engine centre, and you're trying to optimise. But on a regular, day-to-day car, then certainly you're on one side. The difference on a day-to-day car is that I'm 85 kilos in a 1 to 2 tonne vehicle, whereas on the little race car it's 250 kilos. So the driver is 80 kilos plus 250 kilos. It's much more important. But depends what
You
you're
got the
doing.
shockies and all that stuff as well?
Sorry.
You got the shockies and all that stuff as well?
Yeah, on the car inside
That's
that.
what I mean is with your forces and stuff.
Oh yeah, so when we actually do this testing, what we do is lock out the suspension. Right? The main thing that the suspension will actually do on this test is because when the car sits down on the suspension, you've got the same force as when it's, so when it actually comes to rest, you've got the same force on the wheels as the weight of the car. It's just when you hit a bump, it's more relaxed. The area that the suspension damages this testing is if you've got a lot of suspension travel, this is going to squat down at the front and stand up at the back, and it's going to move that centre of gravity a little bit. So the reason that we lock out the suspension on this test is so that it doesn't actually sort of sit down more and sort of exaggerate where the centre of gravity is and wreck our measurements. But in terms of suspension, the suspension components themselves don't actually affect the force balance other than in the transient behaviour after hitting a bump or going around a corner or something like that. Alright, so for this we can calculate V from x1. Cos theta equals x1 dashed on V. Rearrange that. Easy enough. A from this little equation here equals x1, our original x1, minus B, equals x1, and we sub that into it, minus x1 dashed on cos theta. The difference between A and H dashed, tan theta equals A on H dashed, therefore H dashed equals A on tan theta. We've got an equation for A, so we sub that into here. Therefore, H dashed equals x1 minus x1 dashed on cos theta, all divided by tan theta. And then you add the radius. So what we might say is this dimension here is R of tyre. And you can say H equals H dash plus R tyre. H is obviously the ground. We've got our centre of gravity. Right, so there's a lot of steps in there and there's a lot of different maths going on, and how much you find useful is really up to you. I'll provide you the notes and you can go as far or as close as you want on that. The last thing that I'll do is, obviously to do this, we've got an equation for x1 and we've got an equation for h bar and all of these different sub-calculations. And this, we can actually combine all of that into one equation by subbing what we have over there into this one and rearranging. And the version of that equation is h bar equals ray dash L minus ray L on basically the weight or the force down on the whole car, tan theta. Alright, that's an equation. Basically we can use that one equation rather than the couple for that final version. And that's what's in the handout piece of paper I've got for you. Is what we're going to do now. Hopefully they're set up. We'll just go and see if we need to wait at all or whether we're good to go. We're going to fill out these and actually calculate for the car.
Would you consider this to be high school level?
The only thing that's not high school level in terms of the theory involved, I would think would be some of the forces, some of the moments that they haven't done. Now, I guess it's up to you whether you want to expose them to that to get to this other stuff, or whether you want to, simplify this other stuff, just do some experiments and kind of work in some of the algebra or whatever. And I am fully aware that most of this is first year statics in terms of engineering. Now, how far towards that the high school students get in their maths ability, I'm not really equipped to judge on. But this is a simple example that I could come up with that is something we're actually doing experiments with that sort of relates back to the fundamental maths that might, at least to some extent, be useful to you guys, hopefully, at some point. Something simple that you can do on a couple of kitchen scales or something. You should be able to at least tie something like this into it. If only just a board where you do put a weight in there or something like that. But anyway, all right, let's go and see if these guys are prepared for us.